Good day, students. I am Dr. MONIKA KHETARPAL. I am Associate Professor of Physics in Government Dungar College, Bikaner. I am going to deliver a lecture on classical mechanics, which is the first paper of MSc Previous Physics. I am going to start the first unit. In the first unit, we will derive Lagrangian equations, D'Alembert principle, but for that we must know what are constraints. Constraints. Constraints means in Hindi badha. Restriction. That means a constraint motion is a motion which cannot proceed itself in any manner. That means there is a motion of an object which is restricted. For example, I am taking a free particle. The free particle when moves in space, in Cartesian coordinate, we need three coordinates to describe its position. We need x coordinate, y and z coordinate to describe the position of this particle from origin. But what I am doing now, I am restricting the motion of this particle in only one direction. For example, x direction. Then in this case, I will need only one coordinate. Only one coordinate will be needed to specify its position. Earlier, the coordinates needed to specify the position were 3. But now I am using only one coordinate. Hence, by imposing constraints, I am simplifying my mathematical problem. Earlier, which was 3, now it is only one coordinate that is needed to specify the position. Now I am moving over to the another example of constraints. For example, consider a simple pendulum. A simple pendulum consists of a single thread which is inextensible. One end of it is fixed to a rigid support. At the another end, we have a small bob. Now, this simple pendulum, when suspended from the origin and we are oscillating it from its mean position, as I am showing in this diagram, this is its position at some time t, and the angle formed with respect to the origin is theta. Here I am in need of two coordinates r and theta to describe its position. But the motion of bob is not free here, but it takes place under the constraint that distance of the bob, this distance, this is the bob, the distance of the bob from origin, this distance L always remains constant. Here L is the length of the thread which we are taking. That means this equation can be expressed as R equal to L. This is the equation of constraint when we are taking simple pendulum. Now I am taking another example. Another example is of a rigid body. What is a rigid body? Rigid body is a system of particles in which the distance between the constituent particles remain fixed. It cannot vary with time. For example, here as in this diagram, I have taken two particles. First particle is denoted by I, another particle by J. The distance between them is Rij. Now I am imposing some force on this rigid body. Force on this body can change its shape, but the distance between these two particles I and J, that is Rij, will always remain same. That means Rij will be equal to Cij. Cij is constant here. Hence, we are imposing some restriction, some constraint on the motion of the particle, and these constraints are expressed by a equation. For example, I have shown for pendulum R will be equal to L, and for rigid body the distance between the particles Rij will be equal to constant. These constraints are classified as holonomic and non-holonomic constraints. Constraints above said, that means R equal to L expressed by this expression, first expression, and Rij equal to Cij, these two expressions can be written as R minus L equal to 0. This is for simple pendulum, and other, which was for rigid body, can be expressed as Rij minus Cij equal to 0. Here the right hand side is equal to 0 and the left hand side is function of coordinates. That means I am expressing it in the general form as f xyz, t being the time, equal to 0. These constraints, which can be expressed in this form, they are called holonomic constraints. That means constraints expressible as equation 3, they are holonomic constraints. And constraints that cannot be expressed in this form are called non-holonomic constraints. Now I am going to discuss the example of holonomic and non-holonomic constraints. As I have already used the expression R minus L equal to 0. This was the expression of simple pendulum. Hence, simple pendulum is an example of holonomic constraint. And Rij equal to Cij, this was equation of rigid body. Hence, rigid body is an example of holonomic constraint. Now, I am going to discuss the example of non-holonomic constraint. For non-holonomic constraint, I am taking a sphere of radius A as shown by this figure. This is the sphere of radius A. On the surface of this sphere, I am placing a small bob on this sphere. Now I will discuss the motion of this bob on the sphere. Here the equation will be expressed by the relation r square minus a square greater than equal to 0. How this expression has been derived, I am going to tell you now. When the particle, when this bob moves on the surface of the sphere, the distance measured from the origin O will be equal to A. Hence, R will be equal to A. But since this particle cannot always roll on the surface of the sphere, it will ultimately fall under the action of gravity. At that instant, R will be greater than equal to A. Hence, at that condition, there will be inequality sign. Hence, in this expression, there is an inequality sign. Hence, this is an example of non-holonomic constraint. So, here I have classified the constraint on the basis of equation. I am summarizing what I taught you today. Constraint means there was a particle which was initially free. I have imposed some restriction on it. That means its motion has been restricted now. This is a constraint. And there are two types of constraints on the basis of equation. First is holonomic. Holonomic constraints are expressed by the equation function of coordinates equal to 0. And non-holonomic constraints are those constraints which cannot be expressed in this fashion. Thank you, students, for listening.